Okay, so we are now going to talk about the irrationality of zeta 3. And before talking about the proof, we talk about a story behind this theorem. So it's called Irvette's theorem because he's the first person who presented it. And his proof was kind of complicated, more complicated than the one I presented to you about zeta 2k. And later on, there's another guy called Fritz Büchers. He presented a considerably simpler proof than the original one. And we are going to go with his, so that we can understand how complicated this one is. Okay. And now we talk about the story. So by the time he presented this theorem, he was kind of mid-60 or 70. So nobody knew about him before. So he just came to the conference and presented his talk, his theorem, and talked about the proof. And at the time, nobody believed him. It was not until, say, 3 years later, people actually verified this proof and made the conclusion. And later on, Büchers gave a simplified proof. So this is a topic that is quite different from the one I presented you a while ago, because we are not going to compute the number, but we are going to show that the function is irrational. So the number is irrational. I think in analysis 1 tutorials, I think you spoke of, say, the irrationality of square root of 2 or something. Similar here, we are going to do a proof by contradiction. We assume the function is rational, and then we have a contradiction. So before going to zeta 3, we talk about a general principle that leads to the proof by contradiction. So suppose that we have a rational number, and we have another fraction, and we take the difference. We see that the difference is going to be strictly greater than 1 over q times the denominator. And we assume that all the fractions are in the simplest form. So this means that if we were to approximate a rational function by a rational number by another rational, the difference will be something that is around the order of 1 over q. So you can't really go faster. Suppose we have a rapid rational approximation to a real number, then that real number cannot be rational. And we can express this quantitatively using the Dirichlet's theorem. So suppose that x is a real number, and we have a positive number delta, such that we can find infinitely many rational numbers, such that the difference is less than 1 over q raised to 1 plus delta. So this is quicker than 1 over q. If we are slightly quicker, x will be irrational. So that's the kind of proof we are talking about. We want to derive a rapid rational approximation to the number in question so that we can conclude that number is irrational. If you look at the proof of irrationality of E and pi, they are using this principle. And we are going to use this kind of principle for zeta 3 as well. So this is the outline. So instead of double summations, we have double integrals. And we are going to use this double integrals to create a kind of rational approximation to zeta 3. And the way to do it is to evaluate the integral in 2 ways. One way is to show that it's a rational approximation, and the other way to evaluate this integral tells you that the integral is going to decay very fast, so that we can produce a proof by contradiction. And I'll present you the result first. The result is that evaluating the integral one way, we show that this an integer times zeta of 3 minus b divided by some other terms. So this is we can turn this into a difference between zeta 3 and a rational number. So this integral is indeed some kind of rational approximation. And the second step, we are going to show that the integral is going to decay very fast. Well, not exactly the second step. So step 2 is to talk about the rational approximation bit. So if we assume that zeta of 3 is a rational number, then since we can first show that the integral is non-zero, so that this h over k minus the integral is, we kind of have this kind of identity. So this is a difference of integers. So this is just this quantity. A times h over k minus b. We multiply the quantity by k. So that this is a times h minus b times k over k times dn cubed. Because this is a difference of integer that is non-zero. We know that it must be at least 1. So we get like an inequality of some, so it's lower bounded by some strictly positive number. We have a strict lower bound here. And the right hand side is k times dn cubed times this integral. And if we can show that the right hand side can be arbitrarily small, say if this term is less than 1/2, we have a contradiction. So that's the outline of the proof. So we see that it involves two parts. The first part is to talk about rational approximation. The second part is to use some inequalities to get an upper bound, so that we obtain a contradiction. So now this is the first step. So I'm not going to expand all the steps, but if you like really check the details, they will be consistent. I'll just give you an idea. And if you're interested, you can do a full computation. And that will benefit your methods 1 and methods 2 exams. And so first we have the double integral. So originally we are considering the double integral where these two terms are just some polynomials. But we know that the polynomials are just linear combination of the powers of u and the powers of v. So we are going to evaluate this integral by just considering the case when the polynomials are just the powers. So the power of u and the power of v. The idea to evaluate this kind of integrals, especially, well, if you like evaluating integrals, the first time you evaluate integrals is to remember the derivative formula. And afterwards, there are some integrals you can't really find an antiderivative. So in that case, you do power series expansion. And then you interchange the order of summation and integration, and then back and forth, you get a result. And this is what we are going to do here, where we're going to expand this using a power series. So that's just the geometric series. So once we plug this expansion with z equals to uv here, we can turn this integral to a bunch of other integrals. And this other integrals takes the form of that. So that's the kind of integrals we can evaluate. And the way to do this is, the way to evaluate this kind of integral is to use integration by parts.
So you just stand that slide
Yes?
So I don't understand the second line, how it went from the power series of 1 over 1 minus uv to the IRS bit.
You mean the relation between these?
Yeah.
The idea is that I'm going to plug z equals to uv here, and then apply it there. Yeah, I'm going to plug in the geometric series expansion in this integral. So this converts our question to this J.
So it doesn't imply some then, but we're not drawing it because we do it later. Yeah.
Okay, so now we evaluate the integral below. The general way is to set. So this is just a logarithm of product, so we can just turn this into a sum of modes. And the first term is about u, and the second term is about v. So we can just integrate this. And the way to treat this is this integral. So we can just do it right away. This integration by parts. So this logarithm becomes a 1 over v. And you have this dn. Alternatively, you can start with u to the n minus 1, integrate, you get 1 over n, and then you differentiate under integral sign, you can also arrive at the same result.
Oh wait, what's that one type of? In J m n equals 1 over m squared m plus 1 over n m squared.
This actually reflects that the integral is symmetric. Like if you replace
Oh, it's symmetric.
yeah, that's symmetric.
Oh,
And they should be.
Okay, yeah.
So this is just the integral formula for Jn. Since this is a summation involving many different terms, so sometimes n is going to be equal to n, and sometimes n is not equal to n. Oh wait, I think yes, something yes. This should be this should be n squared, and this is 1 over. Yeah. I'll correct the slides and then put it on the website.
Basically massive. So basically
But that's a good observation anyway. It should be m times n squared on the second term. So now we are going to do the summation. Since we have turned the integral into a series of integrals, we need to evaluate the series. So R and S are just some fixed number, but because of the symmetry, so this is the original integral, and because these u and v are just some integration variables, and the whole thing is symmetric, we can, if replacing R, if we just swap the R and S, the integral is still the same thing. It's just remaining the variables. So this means that because we can swap the variables, we can just assume that one variable, the R and S, like, we can just assume that R is less than or equal to S. And when R is equal to S, we are summing over the same indices. Like the numbers here are just the same. So in that case, we are summing over the case when m is equal to n, so that this is 2 over m cubed. So this is the first case. And this is going to give us 1 over n cubed, but for n is when n is very large. So this is just the difference between the infinite sum minus the case when n is less than or equal to r. So this is just zeta 3 minus the first few terms. And when r is not equal to s, we don't really have a closed form expression, but we know that it's a rational number, and we also can give an estimate on the denominator of the number.
Is that just in the limit, sorry, that second line?
You mean this one or that one?
That one.
This one?
Yeah, the equality, the third equality sign, is that only sort of in the limit as
No, it's
R is large?
no, this is not. This is a summation from r plus 1 to infinity. And we're going to express this as a difference from n equals to 1 to infinity and n minus n equals to 1 to r. This is not something in the limit. This is an identity.
Okay.
And for when the case when r is not equal to s, we don't have a closed form expression, but we know that it's a rational number. And we can somehow control the denominator. You can check the details afterwards, but I'm going to present you the result. When r is not equal to s, the summation, we can turn this into a telescoping series, and then we have some cancellation. So that the actual things that is being summed over is a finite sum. And since the terms inside is rational, it's a finite sum of rational, which is also a rational number. And we also know that by some divisibility, we know that if we take the least common multiple of all the integers less than s. So if we take dn to be the least common multiple of all the integers 1 up to n, then the least common multiple of the denominators here is going to divide the square of the least common multiple. So the whole thing, so the denominator of this entire rational number, we can reduce the denominator so that it's a divisor cube of the least common multiple of this quantity. And eventually you can conclude that this integral I, so when r is equal to s, it's going to be 2 times zeta 3 minus some of the first few terms. And when r is not equal to s, it's going to be some integer divided by the cube of this dn. And because we are integrating over the general polynomials, we need to sum over each individual rs. So by at the beginning, we want to integrate a case where this is a polynomial with integer coefficients. So this is polynomial with integer coefficients. And the first step is that we decompose this into a sum of this individual IRS. So to evaluate the original integral, we need to do some summation. And it's essentially a linear combination of these kind of integrals over integers. So, but it's also a finite sum, so we don't need to worry about convergence. So conclusively, if we write this write this polynomial in this way, the integral is just the summation, is just a double summation. But we need to know that this is just some integers. And we can also isolate the case when r is equal to s, and another case when r is not equal to s. And when r is equal to s, we can use the first identity to get a zeta 3. So that's the first expansion. And when r is not equal to s, we just use the fact that it's a integer divided by dn squared, dn cubed. So combining everything, we obtain the first integral expression. Checking anything in those steps will be a worthy exercise, just saying.
I reckon you got this, James.
After the gap.
And now we are going to do the second step. So the first step, we show that the integral is actually a rational approximation to zeta 3. And now we are going to show that the integral, the rational approximation, is going to converge very quickly to derive the contradiction. Yes?
This was meant to be the easy proof, right? Right, okay.
You can now understand the difficulty of the original proof. The original proof, you don't have integrals. You only have some series, and you got a lot of factorials on the numerator and the
Also,
denominator.
like algebra grind.
This is an algebra grind as well.
At least it's got fancy integrals, so it also makes it look better. It's not just like.
Yeah, it looks better, it sounds better. Yeah, so yeah, that's actually the easy proof. So you can see that's how difficult the subject is. So, but the bit before is kind of like the step we completed is kind of the number theorem, the meaning of the integral in number theory. And now we are going to study the properties of integrals using some analysis tools. So this is how analysis and number theory combine together, and that's analytic number theory. So we finished the number theory bits, and now we're going to do the analysis bits. So the analysis bit will be some manipulation of integrals. The series bits are mainly on number theory, so we can see that's how they're connected. And from now on, we just do integrals, no more series, no more summations. So this is the integral formula we begin with, and this is a double integral. But it's not that convenient to treat this logarithm term. It's because you have some convergence issue with near the boundary. Like log of 0, it's not undefined. So to solve this question, we want to convert this double integral into a triple integral. So we start with the identity for log of alpha to the -1 when alpha is greater than 1. When alpha is less than 1, we can. So this just comes from the definition of the logarithm as an integral. And if we do a substitution, and if we do a substitution, we replace v with 1 minus v, we get an integral from 0 to 1 minus alpha. And we can do another round of substitution so that this becomes an integral of this form. As a result, if we move this 1 minus alpha to the left-hand side, we can see that we can replace this with another integral. And this new integral is going to be free of logs. So this step effectively converts our original double integral into a triple integral. And it is this integral that allows us to do some cool inequalities. So now we have 3 integrals. And before doing the estimations, we also need to know what kind of polynomial we have. So analytic number theory is a subject where the mathematicians tend to know a lot of good special functions. So when they want to explore some property, they can pull out a special function that has the exact property. And this guy called Fritz Buchers, he found that this kind of this Legendre polynomial has the property we want. It's a shifted Legendre polynomial.
What property does he want?
So we want to, the property here is that we want to do some integration by parts. So the integration by parts converts an integral to like a boundary term and another integral. And when we want to do integration by parts conveniently, we want to ensure the integrand vanishes on the boundary. So the interval we are working with here are just from 0 to 1. So we want a function that we can do integration by parts many times and also vanishes on the boundary. So that's why we have x times 1 minus x. So we can first look at the integral, the integral that is inside, the u integral. So we are going to integrate u and z first. So that's the first thing we want to do. The idea is that, so if we do integration by parts, we can move this differential operator elsewhere. So the differential operators are originally on this polynomial, and we want to move this on this rational function 1 minus uv times z. This is because the formula for the derivative of this quantity is, well, we can compute this derivative comparatively easy. So if we do all the manipulations, we do all the integration by parts, we can turn this f into the terms inside. We remove all the differential operators and differentiate the function on the denominator. We should arrive at this result. So that's the thing you do after integration by parts. And with the exercise to verify this. So if we plug this identity into the original integral, we see that we successfully removed one f. And now we are going to use the same identity to remove the second f. So the way to do this is to do a tricky substitution that turns this integral into something similar to that. And do the integration by parts again. We have an integral over some elementary functions. And this is where we can start using inequalities. The first bit is to do a lower bound on the denominator. So we have made a substitution here from an integral over uvz into some integral over uvw. So that's why the inequality looks like this. So the first thing is we do a transformation. So this becomes 1 minus w times u times v times w. And there's a familiar inequality relating the arithmetic average and the geometric average. So we are applying the AMGM inequality here. So it's 2 times the square root of the first term times the square root of the second term. So that's how we simplify the denominator. And now we are going to do some, so after we plug this into this integrand, it becomes a bunch of other terms. So we see that this is always something like u to the power, u to some power times 1 minus u, and this is v to some power times 1 minus v. And this is w times w times 1 minus w. So, well, it's not for 0 less than alpha or less than or equal to 1, but this is just if you do the derivative, if you do some differential calculus, you can find that the maximum value of these terms. So the maximum values of this quantity is 1, 4, and the maximum value of these quantities are just 2 over 3 times square root of 3. As a result, we conclude that this q is less than or equal to 1 over 27. And we see that this q is getting exponentiated. So we are actually computing this q to some power. And we know that q is something less than 1. So we see that the integral is actually having some sort of exponential decay. So if we do all the simplification, we see that this integral of f is bounded by 1 over 27 to some power times a constant. If you're interested, you can evaluate this constant. It's going to give you a zeta 2, but that's unimportant for our discussion. So it's less than or equal to a constant times a exponential decay. So now if we look at the other identity we have for the integral. So we see that the integral is involving a term of dn cubed, and dn is just the least common multiple of 1, 2, 3 up to n. So what we are doing here is that we want to bound the quantity dn cubed times I of f. And this is less than or equal to constant times dn cubed times 1 over 27 to the nth power. If we can show that this quantity is going to be less than 1, we can derive our proof. We have the proof of contradiction. But we want to know how fast this dn quantity grows. So this dn is the least common multiple of the first n integers. This is a quite number-theoretic quantity. And to understand the growth of this dn, we are first going to express it. So if p1 up to pk is just the primes less than or equal to n, then the least common multiple is given by this expression. This just means the largest prime power less than or equal to n, like largest power of p1 less than or equal to n, largest power of p2 less than or equal to n, all the way up to the largest prime. So this is the product formula for the least common multiple. And because we know that this logarithm, so p to the log base p of n floor is less than p to log of n over log of p. And p is itself exponential of log of p. So this is just less than or equal to e to the log of n. So this just means that we are going to multiply this term for a couple of times. And the number of times we multiply this term is exactly the number of primes less than or equal to n. So this term is just less than or equal to kn e to the kn times log of n. And this kn is just the number of primes less than or equal to n. And there's this tricky thing called the prime number theorem. It shows that this kn is of order n over log of n. So this means that this kn times log of n is going to be kn times log of n is going to be less than 1 plus epsilon times n when n is sufficiently large. So we are going to use this inequality, that kn times log of n is less than 1 plus epsilon times n when n is large. So this means that the dn is less than e to the 1 plus epsilon times n. So consequently, we have this inequality. So since we are raising this to the third power, so this is less than a constant times e to the 3n times 1 plus epsilon, and we have a 1 over 27 here. So if we combine the terms, it's constant times e to the 1 plus epsilon over 3, raised to the 3nth power. And if epsilon is small enough, the term inside will be less than 1. This number is certainly going to exist because we know that e is less than 3. So we see that this quantity has exponential decay. As a result, when n is sufficiently large, this quantity can be less than 1 over k. So we have 1 less than or equal to ah minus bk less than 1, and that's our contradiction. So zeta 3 will be irrational. And that's our topic. And those are just some books for you to read.
一个特写。
Yeah, we can finish.
Okay.